the second phenomenon of superposition of waves is standing waves. First one we learned it was interference, and now it is standing waves. Now let's first discuss how the standing waves are formed. Now we learned that progressive waves and standing waves are different. Progressive waves have the ability of transferring energy, standing waves do not transfer energy. So there is a question about these waves, whether we can call them waves because they are not transferring energy. Okay. Now standing waves also created because of superposition of waves. All right. So first of all, I'll give you I'll just write down, I'll just say how these are formed, and then I will graphically explain you how the standing waves are formed. Standing waves are formed when two waves which have same amplitude, same frequency, same wavelength, and when they are traveling in opposite direction in the same medium, and when they overlap, that's when the standing waves are formed. Okay. Okay, I have written a lot of things, but let's break that into parts and let's try to understand this. Standing waves are formed when two waves with equal amplitude, frequency and wavelength. So when if you have two waves which have same amplitude, frequency, wavelength, and this part is also important, they should have constant phase difference. The phase difference as the waves move should not change. Okay, the phase difference means, you know, right? The phase difference means if the crest is ahead of the trough, always the crest of one wave should be ahead of the trough. They can't, it can't change, that gap can't change. That's what this means. So if you have two waves which have equal amplitude, equal frequency, equal wavelength and constant phase difference, those two waves can be called coherent waves. Sometimes you might mention about this coherent waves. It's not that hard to understand. It's this. Okay, and they must be traveling in opposite directions. They must be traveling in opposite directions, and when those two waves overlap, okay, they are traveling in opposite directions like this, and then at one point they will overlap, and when they overlap, that is when standing waves are formed. Okay, what are the types of waves? Two waves traveling in opposite directions, but both the waves have same frequency, same amplitude, same wavelength and constant phase difference. Then only these standing waves are formed. Okay, this sounds very plain. So if you want to understand, I have to definitely give you a graphical explanation. So I will use these two colors for two waves, and but we discussed in a particular region of a medium, two waves can't exist. Okay, so two waves can't exist together. Then let's consider the positions of both the waves, and we know they won't exist like that. They will become one single wave because of superposition. Let's draw that and analyze what's going to happen. So let's say this is when they meet first. Okay, both are traveling in opposite directions, you can see, and this is when they meet. Okay, I have just taken initially the trough and trough meeting, sorry, the crest and trough and trough meeting. So when these two are superimposed, you will get a single wave. These two can't exist in this is traveling in this direction, this is in the same medium, both the waves are attempting to travel like this, but we know two waves can't exist like this, so they will combine, undergo superposition, or they will superimpose and form one single wave. I'm going to draw the single wave now. And how is the single wave going to be formed? Crest and crest are meeting, so here the amplitude is going to be large, here the amplitude is also going to be large because trough and trough are meeting. So let's draw it together. These two will result in a wave like this. All right, fine. Now I'd say dark green, maybe this wave, it's going to travel a little to the right, and same amount this wave is going to travel to the left. I hope you understood that. So when this this wave moves little to the right, this wave is going to move little to the left. So what's going to happen? There will be an instance where this trough will another trough will come to this point, and this trough will go to this point. Exactly, right? When this trough goes here, this trough here will go here. If not, we'll consider this part. When this trough goes here, this trough will go here, something like that. Okay, right? Did I make it correct for you? It was accurate. Now when this crest goes here, a trough will be here, and this crest will go to the left, so this trough will come here. So a trough here, trough here. Okay. well, this is what's going to happen next. This will move here, this will move here, this is what's going to happen next. So this time a crest and a crest met. Now here a trough and a trough are meeting, all right, in the corner. So when you combine these two waves and draw the single wave which is going to appear, that is going to look like this. This is how the medium is going to look like now. Okay. So as these two waves move passing each other within that within a confined area, imagine this is going to happen. No? So this part is going to go up, down, up, down. This is the same medium. Okay, a string. Think of a string. So the string is going to go up, down, and when you look at the string, what you actually see is something like this. You will see now this happens alternatively. This keeps on happening. The string going up and down, going up and down. So what you actually see is when now, for example, when a fan rotates fast, when you look at the fan, you will not see the three blades of the fan. You will see just a circle because it keeps rotating fast. Imagine this happens faster. When this happens fast at the same time, then what you will see is this. You will actually see something like this. Okay, when this keeps on happening fast. So this, which appears to us, is what we call standing wave. Okay, all this time I explained what a standing wave is. Now this is not very hard to understand. You will be actually able to see this very clearly. Imagine you have a string. Imagine you have a string and the string is fixed at 2 points. Okay, so the string is stretched. This is a stretched string. So if you pluck that string in the middle, like this, what's going to happen? Two waves are going to be created like this. So first wave will be created and that wave will reflect from here. So you will get these two waves in the same string, but the wave which was generated initially, then the reflected wave. So two waves, same frequency, same amplitude, same wavelength, but in the same medium, but traveling in opposite direction. Then when those two overlap, you will get the standing wave. So how will it look like to you? The string is not going to be like this. It might look like this. This is how the string will look like. Okay, you might have seen this. So it won't see like, you will see like this, it vibrating like this, going up and down soon, because these two happening are going up and down. So this is what you see. This is what you will see. If you want me to draw it a bit more accurate, this is how it's exactly going to appear. The number of loops, now here I have drawn 4 loops, here I have drawn 2, that will depend on the frequency of the standing wave. We'll be discussing about that a little later, but this is how actually a standing wave appears to us. Since we can't draw all these lines, we normally draw a standing wave like this for our convenience. Okay, so this is how the standing wave is actually formed. I've tried my best to explain it as simple as possible. You have everything. You can, if you don't understand it, you can rewind and watch it. Hopefully you will understand, and they will know most of the times, not most of the times, you know, I have seen time to time, they will ask you, explain how a standing wave is formed. This is your answer. You write this and you try to understand that, and how it happens, it's just you have to know it qualitatively, but quantitative analysis, the equations and all those things, we consider only for a wave form like this. Now let's do an analysis, a brief analysis about a standing wave. Now I'm going to take this standing wave. Normally the standing wave, these broken lines are not drawn as broken lines, they are also drawn as complete lines, but let's leave it that way, because it doesn't look like it is, even though it looks like that to us at one glance, it actually does this, it keeps on doing this. So to get that eye feel, I have left it that way. Right, now when a standing wave is formed, even here you were able to see there are certain points. Now if you take these points, they are not moving anywhere. These points, these particles are not moving anywhere, the displacement of those particles are 0. But if you take these particles, the other particles, these particles have displaced maximum. I hope you can understand what I am explaining here, right. So these particles have not moved at all, but these particles, see the green one is at the top, now green one is at the bottom, maximum displacement. There are particles like that. So if I mark them here, these are the particles which did not move much, these particles which did not undergo any displacement at all. Okay, so these particles are called nodes. These are the nodes, these particles I am talking about. So they have 0 displacement, we call them nodes. And at the meantime, there are particles, here these particles, this particle is actually here and here. This was the part, this is where the particle was initially. So I'll mark these points. The points actually are marking in green color. the points, they have maximum displacement. We call them, they are opposite of nodes, so we call them antinodes. So, antinodes are the particles which undergo maximum displacement when a standing wave is formed in a medium. That is the first thing you have to understand, alright, fine. Now, standing wave, we can apply the concepts of waves. So, if you take a particular standing wave, now this is one complete oscillation. I hope you can understand that this is one complete wave here, one complete waveform, right. We have learnt wavelength. So, wavelength will be actually this distance. This distance in a standing wave is the wavelength. You have to be really careful. Okay. For your convenience, I will say now these circular parts we have here, we call them loops. Okay, one loop. So, lambda is going to be distance between two loops. I hope you understood that. Not distance between distance of one loop. No, it's a distance between two loops. So, you can see this is the wavelength, right. So, what is the definition for lambda? I hope you can remember the definition for lambda. Lambda is the distance between two adjacent points which are at the same phase. So, you have to be absolutely careful when you consider two adjacent nodes, they are not at the same phase. Why? If they were at the same phase, what will happen? If they were at the same phase, the distance between them should have been lambda, no? But it is not that way. So, this point, this node and this node are at the same phase. I will mark the nodes. Let us take this as A, let us take this as B, let us take this as C. Okay. So, based on the definition for lambda of a standing wave, A and B are opposite in phase or out of phase, opposite phase or out of phase. Okay. But A and C are in phase. Okay. When you say opposite phase, A and B are in opposite phase, what is going to be the phase difference? That is going to be 180 degrees, if not pi. But if they are in phase or if their phases are same, phi is going to be 0 degrees or 0 radian. Alright. I will draw that a bit larger here, one wave, then we will be able, it will be more convenient for us to analyze this. Right. I have drawn two loops here. This is a standing wave, two loop. Okay, right. So, in that, this distance is lambda. This is very, very important, this part, because we are going to do a lot of questions, calculations and all those things, right. So, what is going to be the distance between within one loop? That is going to be the half of lambda by 2, okay, lambda by 2. And if you take this distance, half of a loop, that is going to be half of lambda by 2, that is lambda by 4. Likewise, in a standing wave, you should know how to define the wavelengths. Okay. In addition to that, let me draw something like this now. Imagine a case like this. Okay. How about this one now? It has 5 loops. If it has 5 loops, what is the wavelength? Lambda by 2, 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 because one loop is lambda by 2 now. So, the total length is going to be 5 lambda by 2. So, likewise, you should be able to identify the wavelengths, and I will make it a little more complex. Imagine there is a standing wave like this. These kind of standing waves also can be formed. We will discuss about that later. See, half of the standing wave. This is also a standing wave, but this is not formed in strings. This is formed in air. Right. So, when you consider this standing wave, what is the wavelength now here? This part, this length in terms of wavelength. Now, this is lambda by 2, this is lambda by 4. So, lambda by 2 plus lambda by 4 is going to be 3 lambda by 4, half and quarter, 3/4. Okay. So, that is the summary of identifying the wavelength. Okay. So, the things we discussed, when you have nodes, the distance between two adjacent nodes is not lambda, that is lambda by 2. That means, adjacent nodes in a standing wave are not at same phase, not in phase. Similarly, adjacent antinodes are also not in phase. Now, if I mark in terms of antinode with the wavelength must be marked like this. See if you can agree with me. This antinode and this antinode one after the other, not the one right next. Now, the length between this and this, it is lambda by 2, because this antinode and this antinode are in they are out of phase, okay, because when you consider this is one wave, okay, right. So that you have to be absolutely sure how to find lambda and all in a standing wave. And then now we are going to discuss, now we discussed about this, when a standing wave is formed, how the particles oscillate at given time intervals. That is what we are going to analyze next, because I feel that is better if we discuss that here. I have taken 3 identical strings, and in each string we are going to create a standing wave, and when the standing wave is created, we are going to analyze how these particles are going to be aligned during the formation of standing waves. So, the reason for choosing 3 strings is this. Now, the strings are stretched and fixed to 2 boundaries. You can see the boundaries in the corners, right? The boundaries in the corner, you can see they are fixed, and these dots you can see are the particles. So, how are they going to move? So, 3 diagrams. In this string, one loop is going to be formed. Okay, one loop is going to be formed, and in this one, let's analyze 2 loops formed, and then here we will say 3 loops formed. That's what we are going to analyze. All right. So, initially, this is the formation of the. This is how the particles are going to look when time is equal to 0. Time is equal to 0. All right. So, first, when you create a vibration here, when you are going to create a vibration here, you are going to create a vibration here. Here, one loop is going to be formed. Here, 2 loops are going to be formed. Here, 3 loops are going to form. So, we know each particle is going to, even in standing waves, every particles in standing waves perform simple harmonic motion. Okay. So, they go up, they come down, they go up again. So, up, down, down, up. That is one complete oscillation. I hope you can remember. Go up, come here, go down, come back here. That is one complete oscillation. So, we have started at t is equal to 0, then t is equal to t by 4, t by 2, 3t by 4, t. That is what we are going to analyze now. So, let us draw the position of each string when time is capital T by 4. That means quarter of the oscillation has, when the quarter of the oscillation has taken place. This is how the particles are going to be arranged when time is T by 4. This is after the first quarter of the oscillation has completed. So, this all of them have gone up. Here it will happen alternatively, one will go up and the other will go down, then only we will get 2 different loops. Here you can see what is happening. Okay. Likewise, for each time interval, let us see what is going to happen. Now, for the second part, when time is equal to capital T by 2, all the particles will come back to their initial position. Here they went up and they will go down. Here went up and then will go down. Here initially it went down and it will go up, right? And it will go down, this will go up. That is what happens. So, a summary, at this point all these particles will actually move downwards, right? Here the particles will be moving downwards, these particles will be going upwards. Here these particles are moving down, these particles are going up, and these particles are going down. That is what is happening. Okay, right. Then this is t equal to t by 2. Next is going to be t equal to 3t by 4. This is how the standing waves are going to look like when time is equal to 3t by 4. So, 3/4 of the oscillation has completed, and so here what has happened, these particles have moved downwards, correct, and this half of the particles have gone down and this half of the particles have actually gone up. Here this half of the particles have gone down, this part of the particles, and this part of the particles have gone up, and this part of the particles have again gone down. That is what is happening here. So, you can see the wave patterns nicely, the way they they are variating, and I have in everything I have drawn the initial position, and again when t is equal to capital T, they will return to their initial position, and after one complete oscillation is completed, the particles will return to their initial position. So, I have explained you for 3 different loops. This is how a standing wave is, and when this happens very fast, it appears as if there is one wave which is fixed at one point, right? That is what appears to us. And when these oscillations happen faster, this is how the standing waves will appear to us. One loop, 2 loops, 3 loops, same string, different types of loops. So, one thing you will observe here is this, look at the amplitudes. As the number of loops increase, the amplitude is reducing. The reason is all the energy here is stored within this loop. So, the amplitude will be high. Here the energy is distributed to 2 loops. So, both the loops will oscillate, not both, yeah, you can consider 2 loops. So, amplitude is less. Here amplitude is distributed even further to 3 parts. So, energy is not concentrated in one single loop like this. So, that is why the amplitude keeps reducing as the number of loops increase. Now, based on this, we can analyze the difference between longitudinal wave and progressive wave, sorry, standing wave and progressive wave. Now, if you take this standing wave, I will use this standing wave for my analysis. Now, we know there are particles. Well, I have not marked all the particles, I have just marked a few. You can see the centermost particle is oscillating at a very high amplitude like this, okay, because it is going up, and then the other particles, the amplitude is relatively smaller than the center particle, okay. So, if you mark the amplitudes, this is how the particles are oscillating with different amplitudes. So, that is the first thing. Now, first this is how the particles are oscillating, right, in this the particles in this string when a standing wave is formed. But we learnt when a progressive wave is formed. Now, this is a standing wave. But when you say a progressive wave, we know a progressive wave is created like this, and when the progressive wave goes forward, it will move to another new position like this, and it will keep on moving forward to new positions like this. We have discussed this before. Right, we will do only one more. Right, good, like this. So, if you take a particular particle, I will choose that particle, say this particle. If you take this particle, it was here initially, now it has gone here, then now it has gone here, now it has gone here, okay. And if you take this particle, right, also this green color particle has actually gone up from this position, right. And if you take the other particle, another particle somewhere here maybe. So, this is the, I am marking it first here because that is the first position, then this is the second position, then the particle has come here. This is the third position, the particle is here, and this is the fourth position, the particle is here. So, every particle in the medium when a progressive wave is formed, it does this, every particle, remember that, this blue color one as well as the green color one. They perform simple harmonic motion at the same frequency, but equal amplitudes. Here, now all the particles have same frequency, they all went up, they all went down, all went up. So, same frequency, but the amplitudes are different. So, in this is standing wave and this one is the progressive wave. So, main difference between standing wave and progressive wave, number one, progressive wave, they have the ability of transferring energy, but standing waves do not transfer energy. That is the main difference. Second one, in standing, when a standing wave is created in a medium, all the particles perform simple harmonic motion at the same frequency, but also at the same amplitude in a progressive way. But in a standing wave, all the particles perform simple harmonic motion at the same frequency, but at different amplitudes. Okay. So, those are the two main differences when it comes to a standing wave and progressive wave. In addition to that, in standing waves we get nodes and antinodes, okay, nodes and antinodes. In a progressive wave we will get crests and troughs, if not rarefactions and compressions. Okay, those are the things, but what we discussed earlier are the most important things. Do not transfer energy, they transfer energy. Here all the particles perform simple harmonic motion at same frequency, but at different amplitudes. But here all the particles in the medium in when a progressive wave is created, perform simple harmonic motion at the same frequency, but at equal amplitudes. So, those two differences are important. I am just dictating it. I want you to listen, understand and make your own notes. That is why I left it there. We will be discussing more about the standing waves later in the other lessons. I hope you understood, got a clear picture about standing wave because based on this. So, these things happen fast, so these will appear to you. This is an introduction to standing waves. And where are standing waves formed? You can create a standing wave in a stretch string. Okay, how do you do that? You have a stretch string. Now, we discussed about a sonometer box. I hope you can remember sonometer box. There is this box where a string goes above two bridges and that string is fixed to one end, and the string will go over a pulley, and then we will connect weights to that string. So, now this string is taut, and then we use a vibrating instrument called tuning fork, and we place it on the sonometer box. So, this tuning fork will be vibrating like this. When the tuning fork vibrates like that on the string, you can see a standing wave being formed like this. Okay, that is an example for standing wave, one standing wave. And the second type of standing wave we can observe is in tubes. Now, you have a tube like this. Imagine you have a tube like this. Okay, and then you bring in a tuning fork and you place the tuning fork like this, and then you vibrate the tuning fork. Okay, so when you vibrate the tuning fork here, the air particles are going to oscillate like this. So, when the air particles oscillate like that, a longitudinal standing wave will be formed inside of tube. Okay, and here you can see this is the string and the particles are oscillating perpendicular. So, this is a transverse standing wave, where this is a longitudinal standing wave. Now, we have done a thorough analysis of the oscillation of particles when a standing wave is formed on a stretch string. This case we have analyzed. We will do the same analysis for the standing wave formed inside a tube. We will do it a bit later. Alright, we will do it in the upcoming tutorials.